Hello, ladies and gentlemen. Root Beer here, and we are looking at question number 3 on the 2007 Euclid Math Contest. What does question 3 have for us? It's 2 parts. 3A. The first term of a sequence is 2007. All right, they're working in the year. Each term, starting with the second, is the sum of the cubes of the digits of the previous term. What is the 2007th term? Okay, so 2007 is it's sort of a big number. And if we're going to be starting to work out this sequence term by term by term, we're going to waste a lot of time if we try and go for just computing the 2007th right from the start to the end. So my guess is there's probably some sort of trick. You know, maybe the sequence repeats after a while. I mean, it might not be strict. You know, it starts going 9, 9, 9, 9, 9. Maybe it'll be something like it goes 9, then 729, then it goes down to 80, then somehow it goes back to 9 or something like that. Look for repeating, because there's no way someone's asking you to figure out the 2007th term of a completely random sequence. There's got to be some sort of pattern to this. So, since we don't really have any intuition as to what the pattern might be, the best thing to do is to just write down the first few terms and see if we notice anything. Okay? Even if we can't figure out what exactly the pattern might be, just writing down the first few terms and correctly computing them demonstrates some knowledge and is likely to get us part marks. Okay? And part marks can always be good, especially if we can't finish off a question. So, sum of the cubes of the digits. So, 2007. And then the next term will be 2 cubed plus 0 cubed plus 0 cubed plus 7 cubed. So that's 8 plus 0 plus 0 plus 343. And that's going to be equal to 351. Okay, 351 is the next term in our sequence. Then what do? 3 cubed plus 5 cubed plus 1 cubed. 3 cubed, 27. 5 cubed, 125. 1 cubed is 1. And this is going to work out to be 153. Okay? And then, well, you might notice, hey, the same numbers have appeared. 153, the order doesn't matter here. We're still cubing the exact same digits. This is going to be 1 plus 125. Plus 27, it's also 153. And 153 is one of only 3 numbers that has this property. This is something I know not because I did this question, but because these are what are called narcissistic numbers. And so the 153, 370 is another one, 371 is another one, and 407. Those are the only 4 3-digit numbers that are equal to the sum of their cubes. So we could ask, the same question with something like 208, and it might end up that we just keep getting 371 eventually. Okay? If you start with any number, you're not just going to work down to these 4 possibilities. As I recall, because I've explored this sort of question a couple of years ago when I was doing a sort of a computing challenge, I think there are cycles you can get where it'll do this number, this number, this number, then back to the first with the exact same pattern. It's interesting stuff to work at. And, that might be a challenge for you if you're good with computer programming. See what you can get when you start with, the first million numbers. Do they all spiral into things like 153? What cycles can I get? Try it with not just adding up the cubes of the digits. Try adding up with the 4th powers, 5th powers. Try it with different bases if you know things like that. That's stuff I've explored in the past. But what we've got here is it's always going to be 153, just returning us back to the problem itself. From this point on, it will always be 153 after the 3rd term. Okay, so our final answer, quite simply, is 153. We don't have to explain this. Okay, an explanation would be, you go to 153, you get 153 back out. It's going to keep doing that. We do just need the final answer. Okay. So no in-depth analysis is required. But if I recall correctly, and this is, I haven't worked at this for a couple of years. It was, I did this computer sort of challenge or investigation. I think anything that is a multiple of 9, might even just be a multiple of 3, will always wind up at 153. Someone out there who's good at computers, double check that, leave a comment, I would love to know. But we are done 3A. Our final answer is 153. That's what it's going to be. That'll be the 2007 term. That'll be the billionth term. Okay. What have we got for B part? Sequence A has nth term n squared minus 10n plus 70. And then they give us the examples of the first 3 terms. 61, 54, 49. Sequence B is an arithmetic sequence with first term 5 and common difference 10. So it starts at 5 and then goes up by 10 each time. So 5, 10, 15, 25, 35, and so on. Determine all n for which the nth term in sequence A is equal to the nth term in sequence B. Interesting. We might be able to make this question harder by asking how many numbers do sequence A and sequence B have in common, which would be interesting. But we're just being asked for the same n, giving us the same number in both sequences. Okay, well that'll just set us up with a very nice sort of equation. We just need to get an equation for the nth term of sequence B and set it equal to the nth term for sequence A. Now, because this guy here is quadratic, I'm expecting 2 answers at most. Okay, but let's see what we can see. So the nth term of sequence A is n squared minus 10n plus 70. Alright, the nth term of sequence B. Now, so sequence B is an arithmetic sequence. It starts with 5 and has a common difference of 10. And all arithmetic sequences have the same style for their nth term. They're always A plus n minus 1 times D. So the nth term of sequence B with an A of 5 and a common difference of 10 is 5 plus n minus 1 times 10. And we can clean that up a little bit to be 10n minus 5. Okay, and we can double check. Plug in 1, you get 5. Plug in 2, we get 15. Plug in 3, we get 25. Okay, we've got them. So now, let's set our formulas equal. We got n squared minus 10n plus 70. I just want to double check I did copy that formula right. N squared minus 10n plus 70. Okay. Is equal to 10n minus 5. Alright, well let's bring everything over to one side and get a nice big quadratic here. So minus 20n, and then the minus 5 will become a plus 5. So we'll get 75 there, and we want that equal to 0. So we want values of n that satisfy this equation. I would expect integer answers, positive integer answers even. So let's see if we can just factor this for a moment. It'd be n something, n something. The minus 75 there. 75 has factors of 3, 5, 15, 25. So let's try 5 and 15, because I know that they multiply to 75 and they add up to 20. So n equals 5 and 15. Now, did they want the terms of the sequence, or did they just want the values of n? Determine all n. Well, there we go. We could even double check if we wanted to. Let's just take n as 5 and sort of do it in our heads. 25 minus 50 is negative 25, plus 70 is 55. And then, 45. And then 10 times 5 is 50, minus 5 is also 45. And we could do the same thing with 15, just grab your calculator. But they just wanted the values of n, so there we go. And we are all done 3B. So as I say, you know, the 3a can actually get quite interesting if you generalize to other forms of narcissistic numbers or just other formulas. I really like the number 40,585 because it's the sum of the factorials of its digits, which is quite cool. You know, leave a comment if you can figure out, verify for me. I think if you start with a number that is this is y9, you will always wind up with 153 if you start the sequence the same way you did in 3a. But other than that, I will see you guys for question number 4 in the next video. Until then, take care.